Hi, I'm Maggie McCracken from the University of Utah, and today I'll be presenting our paper titled A Comparison of the Effects of Older Age on Homing Performance in Real and Virtual Environments. So successful navigation is critical for the independence of our aging adult population. While we typically think of difficulties in navigation, such as getting lost when exploring a new city or going to a new part of town, for older adults, navigation challenges are on a much smaller scale, such as getting from the bedroom to the bathroom, both safely and independently. As our aging adult population grows and more are living alone, the ability to navigate these smaller spaces both improves the quality of life and reduces fall risk. This small-scale navigation is a multisensory process, as the brain uses information from vision, the vestibular system in the inner ear, as well as our body's proprioception. Today, I'll be grouping these last two together and referring to them as body-based self-motion cues. To study how these cues work together, we need a highly controlled environment where we can carefully manage the visual information available. Traditionally, this has been done by conducting navigation tasks in the dark with very dimly lit environmental signs or targets. But with VR, we can now study the same processes in a much more realistic, well-lit environment. The ability to manipulate sensory information in virtual environments raises an important question. Do older and younger adults use sensory cues for navigation the same way across real and virtual environments? To answer this question, we recruited 26 young adults, all between 18 and 30 years old, as well as 19 older adults, all 60 years or older. These participants were all screened for vision, cognitive function, and balance impairments. While these participants completed 2 study visits, one dedicated to the real world and another dedicated solely to virtual reality. It is important to note that while these environments were different, each were completed within the same physical lab space, as well as the landmarks, which are the signs with shapes on them, as well as the targets on the ground, all had the same dimensions and same layout. As far as we can control, participants were completing the same task, but in different environments. The procedure across environments remained the same. So each trial had 3 separate sections, each beginning with an encoding phase in which participants walked to and encoded 3 different locations that were marked by targets on the ground. Participants were informed that we'll have them walk back to that first target they walked to. At the 3rd target, they were then blindfolded for 10 seconds, either by the screen in the HMD going black for the VR condition, or with a physical blindfold for the real world. During these 10 seconds, we did a sensory manipulation, which I will explain in a minute. Once unblindfolded, participants could then walk back to the first location without the help of the targets on the ground. So they're walking back to that first encoded location. We would then mark their response location and walk them back to the start for the next trial. This middle section of each trial, while they were blindfolded, we did one of 4 sensory manipulations affecting the response phase. These 4 manipulations resulted in 4 conditions, each of which had 10 trials each. The first condition was vision only, where participants sat in a swivel chair and were gently spun for 10 seconds. This disoriented the previously encoded body-based cues. Then we had a self-motion condition where the landmarks were removed, so the response phase was completed using only those body-based cues. Then we had a both cues condition, which had no manipulation to vision or self-motion. Both were available during the response phase. And then finally, we had a conflict condition where the landmarks were shifted 15 degrees. This condition is typically used for a type of statistical modeling called Bayesian Q integration modeling. If you want to learn more, we have a paper published from these exact same participants in experimental brain research. I will not be presenting conflicting Q's results today, but instead focusing on the 2 single Q conditions as well as the both Q's multisensory condition. So navigation performance can be examined in both accuracy and variability. The results from this experiment tell the same story across both metrics, so for today, I will just be presenting the accuracy results. Here on the y-axis, we have error, which is the distance between the participant's response location and the actual target location. First, let's look at the real-world results, since this has been the traditional method in small-scale navigation. Across all conditions, participants were less accurate than the younger adults. This finding has been shown in previous research, so we have successfully replicated this age-related difference in the real world. Next, looking separately at the VR accuracy, we see that older adults were less accurate in the single cue conditions. However, there is no age difference when both cues are available. So generally speaking, we are seeing similar age-related differences in the real world. However, this difference is attenuated under that multisensory condition. Age differences aside, when we talk about generalizability, we're also concerned about within-group differences. So in other words, does the same person perform similarly across environments? We are seeing some within-person differences across environment types. Young adults here on the left are less accurate in VR with self-motion cues, while older adults are less accurate in VR under both of the single cue conditions. Regardless of age, everyone is consistent when both cues are available. This we might refer to as a multisensory benefit, where integrating multiple sensory cues leads to a more stable and accurate navigation across environments. So what do these results mean in the broader context of VR research? So first, regardless of age, everyone benefits in VR navigation when multiple sensory cues are available. This is because the multisensory condition was the only condition to consistently show similar performance across environment types. In other words, everyone experiences a multisensory benefit. Next, VR generally captures age-related navigation differences, but navigation depends on the sensory cue availability. For example, we show that older adults have a much harder time navigating under single cues in virtual environments. So navigation techniques such as joysticks, which rely heavily on visual input without corresponding self-motion, may not be as effective navigation technique for older adults. Finally, I also want to mention that the results we present today represent a very small percentage of the aging population. Our participants we refer to as well-aging, as they do not have memory decline and have normal sensory acuity. Additionally, they are able to complete 2 physically and cognitively demanding study visits. With a more representative sample, we would expect any age differences we showed today only to increase. Overall, multisensory cues in VR support successful navigation across many ages, including older adults. This is really important to consider for navigation research, but is especially important to consider for the development of rehabilitation or assistive technology that is geared towards older adult use. On that note, thank you for watching my talk today. I would like to thank my co-authors, Corey, Peter, Jeanine, and Sarah for their help on this paper, as well as our funding sources from the National Science Foundation and the University of Utah Center on Aging. Thank you.